Hello friends, so in this lecture we are going to look at some basic continuous time signals, some signals that we are going to use frequently. So we are just having an introduction of all the signals that we are going to use here and there frequently in the subject. We are going to study about them, a few properties of them, and later as we move on we will see what are the properties they are holding. So first function that we are going to look at is unit step function. So this function is what it names signifies. This is a step of unit, a step of 1 which starts at t is equal to 0. So we are representing this unit step function, unit step signal by ut. So the basic definition of the signal ut is that ut is 1 for positive time and 0 for negative time intervals. Okay, so this is going to be, if I want to represent it, this is going to be 0 for all the time intervals before t is equal to 0 and 1 for all the positive time intervals. So value of this function ut at t is equal to 0 is not defined, or maybe in an absolute sense sometimes you can say that average of the 0 and 1 value of ut at t is equal to 0 is 0.5, but more accurate would be to say that value of ut at t is equal to 0 is not defined. Okay, so this is how we are defining a unit step function. This is 0 for all the negative time intervals and 1 for all the positive time intervals. Now suppose I want to shift this function. I want that this function should have value 1 for all time intervals after t is equal to 2 and should be 0 for all the time before t is equal to 2. Then what I can do is I can just shift this entire function to right by 2 units. Then after t is equal to 2 ut, this function is having value 1, and before t is equal to 2 the function is having value 0. So this function is known as u of t minus 2. This function is being right shifted by 2 units, ut minus 2. Okay, so this is how a general function, suppose I want to generalize this instant be t naught, then this is how ut minus t naught is going to look like. Okay, then we will say that for all the values of, this is how I am going to define ut minus t naught. This is going to be 0 for all the time before t naught and 1 for all the time instants after t is equal to t naught. Okay, so this is how we are defining unit step function. Next function that we are going to look at is unit impulse function. This is unit impulse signal. So what happens in unit impulse signal is, see, this is how we are representing a unit impulse signal. So value of this unit impulse signal is infinity for t is equal to 0. This is defined as when t is equal to 0 and 0 when t is not equal to 0. So for all the time instants other than t is equal to 0, this impulse signal is having 0 value, that is it does not exist. But when t is 0, that is only at the origin, only at t is equal to 0, this function exists and is having an value infinity, value infinite. See, this is not any general function. Why? Because when we define area of this function, area under the signal, we consider it to be 1, but as you can see that any signal which is existing at a single point cannot have area under it as 1. Okay, it is going to have area as 0, but since we are defining that the area under the signal is 1, that is why we say that this is not any normal function, this is a special function. Okay, so we also name it as a general function or Dirac impulse function. So this function is going to be defined as, so we using this unit impulse function for the purpose of sampling, okay. Whenever we are going to convert a continuous time signal into a discrete time sequence, we multiply the continuous time signal with the impulse train only. We are using this signal for sampling. Why? Because this function is existing at single instance of time, single points of time. So when you multiply some other function with this function, we are going to obtain the value of that function at that instance of time. So that is how we can use this function for sampling. Also, one more thing that you can see here is, so these are some properties of delta function, certain properties that you can see. So first property is, if we are integrating another function multiplied with this delta function over an interval of minus infinity to infinity, you are going to yield the value of this function at 0 interval. Fine, so we are going to yield this value at time is equal to 0. Okay, and if we are, if just generalization of this, if the intervals of integration are from a to b, and what happens is, this is going to have the same result phi 0 if 0 lies between a and b, right? If 0 lies in between this interval. If the intervals are something like this, then the result is going to be 0. See, since these intervals are not holding the value 0, they are not enclosing this 0 value, that is why delta t is not going to exist at that point. So when you multiply delta t at any other point, it is going to give 0. Value of delta t at any other point except t is equal to 0 is 0. That is why this happened, okay. And the value is going to be undefined if a is 0 or b is 0. So if either of them is 0, then this integral is going to give you value as 0. Okay, so this is one property that we are using, that we this is also known as shifting property of impulse function. Next property that you can see is, if you are taking this integral, you are taking similar kind of integral, but now what we are considering is, we are considering a shifted, so now we are considering a shifted impulse function. See, this impulse function is going to exist at a single point, which is t is equal to t naught. This is going to exist at only one point, which is t is equal to t naught. So when you are multiplying another function with this shifted impulse function, what happens is, we get the value of this function with this testing function at t naught. At t naught, why? Because this del t minus t naught existed only at a single point, which was somewhere near t naught. Okay, so when you are multiplying another function with this function, you are going to get its value at a single point, which is t naught. So there are several other properties of this delta function that we can see. So when we are scaling this function, when we are trying to time scale this function, time scaling means, if I just multiply this constant a with the time inside this argument, then what happens is, why? Because see, this delta t is occurring only for t is equal to 0, okay. This is not occurring for any other values of time. So when you are doing this time shifting, time scaling, when you are performing this time scaling, what happens is, this value comes out and affects the area, because you know that area of this function is going to be 1 only, okay. If I just expand this function, suppose I just expand this function to minus epsilon to epsilon, right. So to the area of this function to remain unity only, the length of this rectangle is going to be 1 by epsilon, okay. Only if the length of this 1 by 2 of psi ln. Only if the length of height of this rectangle is 1 by 2 of psi ln, only then the area under this curve is going to be unity. So for this to be 1 by 2 of psi ln, this is what I am saying, whenever you are scaling in time, this 1 by psi ln is going to come in denominator here. Okay, so this is a property that this impulse function is following. And if we are performing time reversal, then this time reversal is not going to affect this function, right? Even here you can see we just putting a equal to -1. So what happens is mod of -1 is 1, which means that this function is not going to be affected by time reversal. Why? Because this function is existing only at a single point. If you are performing time reversal, then there is no swapping, no switching is possible. That is why time reversal does not affect delta function, right? Then there is one more property known as sampling, which is, so what happens when you are multiplying any function with this delta function, what happens is you are going to have the sample of the function at time is equal to 0 and delta function. Similarly, if you multiply any function with the time shifted delta function, you are going to have sample of that function at the shifted time into the delta function itself. Fine. So these are some of the properties of the impulse function. So we are going to regularly use this impulse function. This is an important signal in the subject. So you can just remember all the properties of impulse function. So the next signal that we are going to look at is unit ramp signal. Unit ramp signal. So this is basically a linearly increasing ramp. We are representing this by RT, and what happens in this signal is, this is how unit ramp signal is going to look like. So what happens in this signal is, whenever its value is greater than 0, that is for all positive time intervals, value of this function is going to be equal to t. That is the slope of this line. Okay, this is just a slope of line of slope unity. This is just a line of slope unity. Okay, so this is how we are representing this function, and it's going to be 0 for time less than 0. So similarly, as we have seen in unit step signal and delta signals, this function can be shifted to any other point. Suppose I am required to draw r of t minus t naught, and this function is going to shift right by t naught. So this is how r of t minus t naught is going to look. Okay, so this is how ramp signal is going to look. Now the three signals that we have just studied, impulse, unit step and unit ramp, all these signals are related to each other. How they are related? See, this signal, this ramp signal, this is having a slope of unity, right? The slope of this signal is unity. So when I am going to differentiate this signal, differentiating a signal means you are obtaining the slope of that signal. So when I am going to differentiate this signal, I am going to get a unit step signal. Why? Because slope of this signal, slope of this line is unity. So when you differentiate a ramp signal, you are going to get a step signal, and vice versa. When you are going to integrate a step signal, then you are going to get a ramp signal. Similarly, when I am going to differentiate a unit step signal, see what does the slope signify? That how is this function changing, how is the signal steeping up. Okay, so whenever you are going to differentiate a unit step signal, you are going to get an impulse at that point. Why? Because slope of a unit step signal, see this is how a unit step signal looks like. Right. So slope of this line is changing steeply at t is equal to 0, right? Slope of the line is changing at t is equal to 0. That is why, and how much is the change in slope? What is the change in slope? Infinite, because this is a line parallel to y-axis. So what happens is, whenever I am going to differentiate a unit step signal, I am going to obtain impulse at that point. Okay, so now we are going to look at next signal. So the next signal that we'll look at is complex exponential signal. So we are defining a signal xt as e to the power j omega t. So this is a C, since this signal is having j here, so this is going to be a complex signal. We are having an e exponent here, so this is an exponential signal. So this is known as a complex exponential signal. And as we've already discussed, using Euler's formula, this e to the power j omega t can be written as cos omega t plus j sin omega t. Cos omega t plus j sin omega t. So this cos omega t is going to be the real part of this signal, whereas this j sin omega t is going to be its imaginary complex or exponential, whatever you say, imaginary part. So this is going to be the imaginary part of the signal. So we cannot represent it graphically because this is a complex signal. It is having some imaginary part which we cannot draw. But for just now, you can just remember that we are having a complex exponential signal which is of the form e to the power j theta or e to the power j omega t, and we are going to use this signal quite often. So just remember it. Next signal that we are going to look at is sinusoidal signal. Most of you would be aware of this signal though. But we're just going to look at it right now. So most commonly used sinusoidal signals that we encounter are going to be sine and cos. So this is how a sine signal is going to look like. And this is how a cos signal is going to look. So this is how a cos signal is going to look like. So this sine is having its zero crossover. Zero crossovers means whenever this signal is going to have its value as 0. This is having its zero crossovers at 0, pi, 2 pi, or generalizing, I can say that zero crossovers for sine signals going to occur at k pi, where k can be 0, 1, 2 or any integer, right? Okay, so this signal is going to continue in the negative direction also, fine. Now zero crossovers for this cos t is going to occur at pi by 2, 3 pi by 2 and so on. Okay, so this is going to have value 0 at pi by 2, then 3 pi by 2, 5 pi by 2 and so on, fine. So these are basic sinusoidal signals. Most of you would be aware of them already. Okay. So if I am just required to tell about the time period of these signals, I am going to tell them as 2 pi. Right, time period of these signals is going to be 2 pi. See, if I am expressing them as argument as only t, then I am taking the time period as 2 pi. Suppose I would have expressed the argument as sine of omega t, then the time period would have been, okay, just look at it here. If I would have taken the signal as sine omega naught t, then time period would have been 2 pi by omega naught. 2 pi by omega naught, okay. So this is how you're going to find out the time period for these signals. Also we can express these signals as complex exponential signals or some coefficients of constant exponential signals, complex exponential signals, right? Like sine omega t can be written as e to the power I theta minus e to the power minus I theta. Okay, so we're going to look at it later. For now you can just remember that these are some basic continuous time signals. In next video, we're going to look at some basic discrete time signals, and after that, we're going to look at some operations on signals.